6.1, the exponential function and its inverse. So exponents are a class of functions different from polynomials. With exponential functions, the exponent varies while the base remains the same. With polynomial functions, the base varies while the exponent remains constant. So we're going to be looking at exponential functions. Y equals b to the x. X is the exponent. Okay, and some things about the exponential function we must know is that the base cannot be equal to 1, right? If it was equal to 1, then you would have 1 to the x, which is always going to be a 1, which is a constant function, a linear function. So the exponential does not work with a base of 1. But for other bases that are not 1, we can consider. Okay. Bases not 1, but are still greater than 0. So not negative either. The domain of the exponential function being every real number, and the range of this exponential function being y greater than 0. And we'll find that the y-intercept of the exponential function is 1. And then for other exponential functions that we'll explore, that y-intercept will be related to the value of a. And so we'll be looking particularly at functions that are expressed as y equals a times b to the x. And the exponential function also has a horizontal asymptote. So we will be looking at exponential functions that are increasing. So exponential functions that are increasing are what we call exponential growth. You may recall that from your grade 11 course. Okay, and so as x gets larger, the value of y grows to a very large positive number, and you see a growing graph that looks like this. We have also exponentially decreasing functions, and this occurs when the base of your function is a number between 0 and 1. So it includes decimals, 0.1, 0.5, etc. And we call this kind of function a function that is a decay function or exponential decay. And that means that as x becomes large, for larger values of x, to read the graph from left to right, the value of the y value of the function will decrease and approach 0. Okay, but it will not cross 0, hence why we have a horizontal asymptote at the x-axis. Okay. All right. Let's spend some time reviewing inverse functions. The inverse of a function is the set of ordered pairs obtained by interchanging the members of each ordered pair of the function. So ways we can find the inverse function. 1, we can interchange the ordered pairs. So for example, if we had a function f of x, and I define the function as just a set of ordered pairs. So you can see I'm using set notation here with the curly brace brackets, and including some ordered pairs. So here's some ordered pairs, x, y coordinates, right? 1, 2, 3, 4, and 5, 6. The inverse function, and we use this notation, f with a -1 as a superscript, right? A -1 is a superscript, not an exponent, it's a superscript. Okay, and I can obtain the inverse function by simply interchanging the ordered pairs, right? So what was xy in the ordered pair in the function becomes yx in the inverse function. So this set for the inverse function would be 2, 1, 4, 3, and 6, 5. Algebraically, we can also interchange x and y and resolve for y. So example, if I had a function y equals 3x plus 12, then the inverse of this function would start off by interchanging x and y. So now I have x instead of y equals 3y instead of 3x plus 12. And then like all functions, we have to write y in terms of x. So we kind of resolve for y or isolate for y. And so if I subtract 12 from both sides, I get x minus 12 equals 3y. And then if I divide both sides by 3, I get 1 over 3x minus 4 equal to y. And then I just replace y with our inverse function notation. So the inverse function equals x over 3 minus 4. We can also obtain the inverse by looking at graphs. And so the inverse of a function is a function that is reflective or reflected on the line y equals x. So if I sketch a function such as a parabola of x, I can obtain the inverse function by looking at the line y equals x and treat that as the mirror line for my inverse function. So I'd have an inverse function that looks something like this. It's a function that is the mirrored reflection of f of x along that y equals x line, that red line. Let's call this the inverse. This is f inverse of x. Okay. And number 4, we can also interchange the restrictions on the domain and range of our function. So if we have a function f of x, and let's say the domain of this function is square bracket 0 and 5 round bracket, and the range for this function is -1 and 10. 1 round bracket around -1 and square bracket around 10. For the inverse function, the domain of the inverse function would just be the range of the function. So my domain takes on the interval -1 round bracket to 10, including 10 square bracket. And the range for the inverse function will be the domain of the function. So the range here is 0 to 5, inclusive of 0, but not inclusive of 5. So square bracket for 0 and round bracket for. Okay. So that's a little bit of that review for inverse functions. Let's apply it to the inverse exponential function. So if you look at if we look at the function y equals b to the x, and I wanted to find its inverse, I would interchange x and y, and so I would express this as x equals b to the y. Okay, and so the inverse exponential function has some properties, right? So the domain takes on the range of the exponential function. So if the range of the exponential function was y greater than 0, then the domain of the inverse would be x greater than 0. The range, well, if it takes on the domain of the original exponential function, so if the exponential function had a domain of every real number, and so the range of the inverse will be every real number. The x-intercept, another property at x equals 1, and that's just simply from the idea that this is a reflection of the exponential function. And instead of a horizontal asymptote, we're going to have a vertical asymptote at x equals 0. So I should say y-axis. And essentially what we're going to see is that the exponential function is just reflected over the line y equals x to obtain the inverse function, x equals b to the y. And so here's that graph now. For increasing functions, so again, here is that line y equals x in red, and you can see that here is the increasing exponential function highlighted in yellow, and its mirrored reflection is the inverse. Okay, and for decreasing functions, here in yellow, I'm highlighting the decreasing exponential function. And then if I, again, highlight the line y equals x, I would have mirrored the graph of the inverse function. Okay, and as you can see, mirrored points, such as the y-intercept on the exponential function, which is a 1, gets mirrored over and becomes the x-intercept on the inverse. Similarly here on this graph too. Okay, so again, some of the characteristics of an exponential function when we talk about what we talk about here, b is the base, x is the, well, actually, this should be corrected. X is the exponent, and b to the x is what we call the whole power. Okay? So some examples to go through. Using the following exponential graphs to answer the following questions. So we can see y equals 0. There is no curve here. It's just the 0 line, the x-axis. If I use, again, series of graphs here where b values are less than 1, between 0 and 1, so 0.6 and 0.8, these are decreasing or decaying exponential graphs. And then once the base reaches 1, like I said, that's not an exponential graph, that's a straight line. And then above 1, we have some slowly growing graphs getting more steeper and steeper as you increase the value of b above, well above 1. So we can answer some questions here. Part A, what effect does changing b have on the graph of the exponential? Well, if b is greater than 1, then a bigger b value is more steep. Okay, or in other words, grows faster. Right, so you can see that here, right? So 1.2, 2.5, 5, 10, these bases are getting bigger and bigger and bigger. And as you go from left to right, and you can see the steepness getting steeper, steeper, steeper. It's growing much faster. In the case where b is less than 1, well, you can see as b gets closer and closer, from a 0 closer to 1, the graph gets less and less steep. Okay, so for 0 to b to 1, the graph, gets less steep until you reach a flat horizontal line at 1. Okay, so less steep, or you can say it's a slower. Okay, so part B, what is the y-intercept of the graph? Does it depend on the value b? Well, the y-intercept of the graph, if you notice, what is the meaning of the y-intercept? Well, that's when the x is 0, right? And in all cases, anything raised to the power of 0 is going to be 1. All these graphs share a y-intercept of 1. So let's say here always 0 and 1. What happens when b equals 1? So we're just going to formally write down what I've already said to you earlier here in the lesson, and that when you have the base is equal to 1, you get y equals 1 to the x, right? And that which is always, this is always 1, right? A flat horizontal line, not an exponential function. And then when b is less than 1, why does the graph decrease as x increases? Right, so take for an example, y equals 1/2 to the power of x. Right, so if you let x equals 2, then what is y? Y equals 1/2 times 1/2. Okay, if I let x equals 3, then y is equal to 1/2 times 1/2 times 1/2. Right, so as I increase the value of x, I'm just adding another 1/2 to keep multiplying. So if you take half of a 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 half, eventually you're going to approach 0. It's getting smaller. The graph decreases. Okay, let's look at number 2. Construct a table of values for x equals 1, 2, 3, 4, 5. All right, and compare the first differences for the functions y equals 3x, a linear function, y equals 3x squared, a quadratic function, and y equals 3 to the power of x. Here's our exponential function. Describe the rate of change for each. So let's quickly fill in some of these values. So x equals 1, 2, 3, 4, 5. Okay. And then for the y values, I want you to fill in the corresponding y values using the functions above. Pause the video, take a few moments to do that. Okay, so hopefully you've had a chance to fill in those values. So here they are, the values for 3x, 3x squared, and 3 to the power of x. I want you to try and take a few moments to do the first differences. Pause the video now. Okay, so here, hopefully you got a chance to do this. So you can see for the linear function y equals 3x, the first differences have a constant value of 3. Okay, this constant rate of change, 3, is the slope of the line. Okay, so something that hopefully we remember from grade 9. For the quadratic function y equals 3x squared, the first differences increase by 6 each time. So your second differences are 6. This is a quadratic. The first differences are not constant. And for the exponential function 3 to the x, the first differences increase by a factor of 3 each time. What does that mean? Oh, well, if you look at the first differences, 6, 18, 54, and 1 is 62. What is 6? Well, 6 is just 2 times 3 to the 1. And then 18 is, well, let's put another factor of 3s, right? 2 times 3 squared. What about 54? 2 times 3 to the power of 3. The last one, 2 times 3 to the power of 4. Just keep multiplying by another factor of 3. Okay, let's look at number 3. Determine the equation of the function and sketch its inverse. All right, so when you try to determine the function, the form we're going to use is y equals a times b to the x. Okay, and what you have to remember is that, yes, b is your base, and a is your y-intercept, okay, or initial value. Now, in order to determine the base, you're going to need to look at consecutive y values, right? So let's look at the y values. And consecutive y values starting from the y-intercept. So here we have 1, and then it jumps to a 3, right? So, and then after 3, it jumps to a 9, right? It's a factor of 3 each time. Right? Can I write each number as a factor of 3? Like 1 is just 3 to the power of 0. Okay. And 3 is just 3 to the power of 1. And 9 is just 3 squared. 0, 1, 2, right? So the base I can use for this exponential function is 3. So b equals 3. I can just look at the ratios, right? So again, 9 over 3 equals 3, and then 3 over 1 equals 3. So a common ratio between the consecutive y values. So a couple of ways we can look at how to get that base. So looking at my equation, right, it's going to be y equals a times 3 to the x. What is a? Right, you can substitute a known point, okay, or you can look if you have given the y-intercept. The y-intercept is just 1, so a is going to be 1. But if you wanted to do this algebraically, you'd substitute a known point. You could try 1 and 3, right? So you could use 1 and 3 and determine it. So y value is 3, a times 3 to the power of x, where x is 1. And so 3 equals a times 3, which means 3 over 3 is equal to a, and then a is equal to 1. So there we could confirm a equals 1. So therefore, the equation is y equals 3 to the x. Now, what if I wanted to graph the inverse Well, I would just take some of these points like 0 and 1 and then switch them around. So 0, 1 becomes 1, 0. 3 and 1 becomes, 1 and 3 becomes 3 and 1. And 9 and 2 becomes, 2 and 9 becomes 9 and 2, which I can't plot on this graph, but I can sort of show some of that inverse looking like this. And then I could kind of show you that y equals x line as the line of symmetry. Okay. Looking at example 2, we have an example of a decaying function, right? This is a decreasing exponential function. Okay, so we're going to use, now you can use a couple of ways you can do this. You can use b values that are between 0 and 1, or you can use b values that are greater than 1, but use an exponent of a negative x. Okay, so if I look at the ratio between consecutive y values here, so I have 16 and 4, right? So 16 over 4 equals 4. And then 4 and 1, right? 4 over 1 equals 1. Sorry, 4 over 1 equals 4. So consecutive ratios are the same, 4. So I could express my function as a power of 4. Right? So I could I would use that y equals a times 4 to the power of negative x as my function. Okay, as one way of doing it. But generally, we know that we don't like expressing things as negative exponents. I could express the positive exponent of this. And so recall that the positive exponent is obtained by taking the reciprocal of the base. And so I could express this function as y equals a times 4 becomes 1 over 4 to the power of x. Okay, and so this further confirms that, hey, we have a decreasing exponential function. Our base value is now a number between 0 and 1. Okay, and then I can use a coordinate such as negative 1 and 4 to find a. Okay, so 4 equals a times 1 over 4 to the power of negative 1. And solving for a, we would have to flip the fraction back to a 4. So 4 equals a times 4 to make that a positive 1. And then all this says is that a is equal to 1. So you didn't actually have to do all this work if you're given the y-intercept. Hey, the y-intercept is 1. That's our starting value, our initial value, and we can use that for the function. So the function, therefore, is y equals 1 over 4 to the power of x. Okay, and so let's graph the inverse. What I forgot to mention in the last graph. What is the inverse here, right? So I didn't write it down. So the inverse function is x. So if you flip the x and y, right? So y equals 3 to the x is then equals to 3 to the y. And I want to isolate this in terms of y in terms of x again. So how do I express that? And we use something called a logarithm. Now, a logarithm is what we call the inverse function of an exponential, right? So if I wrote here y equals log of base 3 of x, this will tell me, right? I want to know the log of some base 3 of some number will give me the exponent y, the exponent that I have to use on 3, right? So again, 3 to raise to some exponent y is equal to some value that you evaluate. 3 to the power of 2 is 9, right? Let's use a concrete example, right? So 3 to the power of 2 equals 9. Or I can express this using logarithms as the log of base 3 of 9 equals to 2, right? So this says if I had the answer that I evaluate here is the exponent, right? What exponent do I need to apply to this base 3 so that I can get the logarithm argument 9? Okay. All right, sorry, so back to this one. Y equals 1/4 to the power of x. Now I can express this as, if I take the inverse function, so the inverse function would be, let's flip them around, x equals 1/4 to the power of y. Okay, but then I'm going to use logarithms here, right? I need to express this inverse using a logarithm so that I have y in terms of x. So y equals a log, and I write the base as a subscript, so 1/4 of x. Okay, and so this tells me again that y is, what is the exponent y? So that if I use the base of 1/4, and I raise that 1/4 to the exponent y, I will get the argument here for logarithm x, whatever x is. Okay, exactly what's being expressed here, right? So 1/4 raised to some power of y will give me x. So this is the inverse function. This logarithm is what we call the inverse function of an exponent. Okay, in terms of graphing this, I can just again interchange the x and y. So for -1 and 4 becomes 4 and -1, and 0 and 1 become 1 and 0. Okay, and you can plot your line, y equals x line, and then we mirror it, right? So we mirror this. So remember, we have the inverse function has a vertical asymptote, not a horizontal asymptote. So I have to stop here at the vertical axis and get a function that looks something like that. Okay, moving right along, number 4, determine which is an exponential function. And we can do this by looking at the first differences, second differences, to see if they're linear or quadratic. And if they're not, we check to see if there is a common ratio, right? So if I looked at the first differences here for the first one, we have 8 minus 2, which is 6, 18 minus 8, which is 10, and 24 minus 18, which is 6. And then if I take the second differences, I got 4 and -4. Oh, neither are linear or quadratic. Oh, interesting. So check if there's a common factor, right? So let's see. 8 divided by 2 equals 4. 18 divided by 8, oh, not equal to 4. No common factor, right? Even if I look at the first differences. So I think, well, formally we look at the first differences. Is there a common factor there, right? 10/6 equals what? So second number minus divided by the first number. And looking at the second pair, 6 divided by 10. Not the same. So no common factor. Not exponential. Okay. Looking at the second table here, something a little bit more obvious, right? Like let's just take the first differences first, right? 25 minus 5 is 20. 125 minus 25 is 100, and then 625 minus 125 is 500. And now we can see, hey, yeah, there is a common ratio between these numbers. 100 divided by 20 is 5. And 500 divided by 100 is 5. Common ratio of 5. So the first difference is increased by a factor of 5 each time. So this is going to be an exponential function, and your base is going to be 5. Okay, and so for basis 5, we can say here y equals a times 5 to the x. Okay, and what is our initial value? Well, we got to solve for that. So let's say use 2 and 25 as one of our points. We can use any of the points we like, but I'll use 2 and 25. So 25 equals a times 5 to the power of 2. So 5 squared is 25. And so 25 equals a times 25. And so a equals 1. When we solve this, meaning therefore our equation is going to be y equals 5 to the x. Okay. And then on to our last example. Complete the table of values, or table for the key features of this following function. F of x equals 1 over 2 to the power of x. And its inverse. Okay. So we have a decreasing exponential function or a decaying exponential function. The domain of this function is every real number. Okay. And the range of this function, remember, for an exponential function, we have a horizontal asymptote on the x-axis. So the y value is going to be greater than 0. With the horizontal asymptote, we have no x-intercepts. And we do have a y-intercept. That's the starting point, the initial value is 0 and 1. And then where is the function positive? Well, the function, so think about a decaying exponential always has positive y values, right? Here's our functions above the x-axis everywhere. So every real number. Are there any points where it's negative? No, there are none, no intervals. What about where the function is increasing? Remember the difference between positive and negative and increasing and decreasing? Talking about increasing, think about drawing the direction arrows as you read the graph from left to right. And you can see these arrows are going down. So it is decreasing everywhere. So for every real value x, it is decreasing, but there is no part of the graph where it is increasing. And at the very last table here, the equation of the asymptote is the horizontal asymptote, y equals 0. Right? Now, if we were to take the inverse, things are interesting, right? The domain of the function is the range of the inverse. So now I'm going to write here, y is every real number, right? And the range of the original function becomes the domain of the inverse. So it's going to be x greater than 0. The y-intercept gets reflected on the line on the y equals x line, so the y-intercept becomes 1 and 0, which is the x-intercept of the inverse. If there's no x-intercept in their function, then there is no y-intercept of the inverse. Okay. And so for the rest of this, I'm going to just show you a plot of the graph of the inverse function, right? So here it is. So x equals 1/2 the power of y can be written in logarithmic form. Y equals log of 0.5, log of the base of 0.5, and an argument of x. And here it is. Okay. So you have the y axis as the vertical asymptote. And we can answer the rest of the questions, right? Where is this function positive? And so it is positive right up until the x-intercept over here, right? You can see its y values are positive and right until it reaches the x-intercept of 1 and 0. So I would say here it's going to be 0 less than x less than 1. Where is it negative? Well, it's going to be after the 1, right? So x greater than 1. And then what about increasing and decreasing? So again, if I draw the guiding lines, direction lines, reading the graph from left to right, it looks like the function is decreasing everywhere, right? The function is decreasing everywhere on the graph, not for all x. I'm saying on the graph is decreasing everywhere. So what x values does that represent? That represents every x value that is to the right of the vertical asymptote. So x greater than 0. Okay. Is the function increasing anywhere? Nope. So none. And the equation of the asymptote is the equation x equals 0. Okay, so there you have it. As you're doing problems in this section, look at what look at the graphs that you have, plot them on Desmos, plot the inverses, get a better sense of what these graphs' characteristics are, especially in relation to their parent exponential functions. Okay, so that ends this lesson.